Thanks so much. It's really a great honor to be here, and thanks so much for your guys' interest in our deep learning solutions and systems. At Facebook, we use a lot of them that I'm going to be talking about. I think I was thinking about what kind of things I should talk about in this meetup, and we just released Caffe2 as of a few months ago, and I think it would be nice for us to share a little bit of story of how we use Caffe2 inside Facebook, and what kind of things we're thinking about developing and contributing to the community, and then basically, hand over to Puya and to Bram to talk about the server-side optimization and mobile-side optimization. And one thing that we're really excited about is to have the opportunity to talk to everyone and basically listen to your feedbacks about what kind of things you found good, what kind of things you found bad, and basically obtain feedbacks for us to further improve the developer stories, the Caffe2 framework, and also to basically push forward the nice applications of all those deep learning things, right? So it kind of was started, in the back in the grad school days where we want to implement stuff and things like that. What happens is that from the research side and from the product side, we have varied needs for different kind of ML applications. And from the research side, we need to design flexible ML algorithms, and we need to, basically push forward research by making everything reproducible and things like that. And in products, what we constantly find is that we want to apply machine learning and deep learning in different applications, and we will need a way for us to more easily represent models and ship models at a very high performance and very high flexibility. Now, over the years, what we found is that there is, a very interesting a spectrum of different needs from the research side and from industry side. And we have Facebook AI Research that is basically conducting much cutting-edge research that will probably be 5 or 10 years down the road. And we have applied machine learning, which I am at, that takes care of the whole product side. And so the flexibility on the research side and also the stability and the high performance need from the industry side actually triggers us to think about, a dual play of deep learning frameworks. And today, what we're basically trying to do at Facebook is that we're using two deep learning libraries, PyTorch coming from FAIR and Caffe2 from an ML, that basically works together to cover the wide spectrum of use cases inside Facebook. And we're hoping that these kind of models could help the external world to also push forward the two sides as well. So what is Caffe2? It is essentially a DNN framework that we designed to free people and free, Facebook engineers and also general engineers from the exact logistics of how to set up the deep learning environments, how to represent the model, and to focus on shipping things into the products rather than dealing with all those kind of builds details and things like that. What it does is we use Caffe2 to provide a very lightweight framework for machine learning and specifically computer vision algorithms. And it's primarily designed for production use cases, meaning that we care quite a lot about the speed. We'll be showing that it runs really fast on the server side and the mobile side. And we provide a C++ and Python-based interface for people to put into different applications. Inside Facebook, we usually mostly use C++ due to a lot of high-performance use cases. But Python becomes very popular when we want to very quickly iterate models and think about designing models and things like that. We support deployment onto different platforms. At Facebook, so far, we have been deploying things on our cloud side, on our server side, on our local laptops, on iOS and Android, and actually they are actually running on all these Facebook apps that you have on your phone today, maybe. And we provided Windows support. Haven't really tried it, solidly tested it, but it builds, and we've got feedback that actually runs. In terms of hardware, it also runs on different IoT devices, such as Raspberry Pi and Tegra X1 and things like that, which hopefully will be useful for applications such as self-driving cars. So inside Facebook, what we use it to drive computer vision applications, and quite a lot of them, like image understanding, classification, and for machine translation, using recurrent neural nets and things like that, for speech recognition, and for a lot of ranking systems where we want to rank the relevance, the interestedness of the different stories on Facebook and things like that. And it's pretty much running 24/7, giving us quite a lot of pressure to make sure that the system is solidly working and not breaking. And it's also driving quite a bunch of research. And earlier this year in Feb, we have this paper called Mask RCNN, focusing on using like similar detection and segmentation approaches, but providing a much better performance than previous approaches to do object detection, segmentation, and things like that. The Mask RCNN paper is out. I think Ras is going to be putting out his code as well in Caffe2 so that we can share it at more detail. What I wanted to share is basically, we've heard quite a lot of stories since last October about, neural style transfers on the phone, right? And it's kind of like probably become a buzzword and maybe a little bit of a fad. But I want to basically use this as an example of how we used Caffe2 in driving a product from the inception of the idea to actually getting it into the products. So this is what we had back in last June, I think. So we had this idea that we should put style transfer onto the phones. And we were like, let's take a model that's like from those papers and let's try to put it on the mobile side with our Caffe2 runtime. And what we were able to do back then was to have this very tiny, teeny box, 128 by 128, and put a Lego model on top of that and basically say, here is what you can have a taste about the style transfer, and most likely, back then we were thinking it wouldn't be possible for us to do it real time. And we're like, we could provide you this little preview, and then once you take a photo, we can go through a 5-second post-processing and give you the full picture rendering effects, right? Now, it turns out that by a bunch of techniques and finding better model architecture for these models, and do a bunch of numerical optimizations on the runtime side, and also to compress models so that we can cope with the very small footprint requirements for the mobile platforms, we're actually able to achieve a much better performance that I'll show later. So in terms of model architecture, we kind of started with AlexNet, right, which is basically the 2012 deep learning model that started the whole field. And the problem with AlexNet is it's too big. Right? All those huge FC layers on the top and the model being 240 megabytes really made it tricky to do mobile deployments and even server deployments. Now we kind of follow that a little bit on the next year after AlexNet VGGNet comes out. The performance gets better, but the model gets even bigger. And it's really nice for platforms where we don't really care about the model sizes, things like that. But that was a bit tricky to push, even trickier to push on the mobile side. So GoogleNet came into play, and it was actually very nice because it improved performance and it actually drastically reduced the model size. And so all these kind of inception modules achieved a very good effect, which is extracting information from different levels and different scales, and making it possible that the whole model gets down to about 24 megabytes, still achieving a much higher performance than VGGNet. And we came with more interesting network structures such as ResNet from Kaimin, and also ResNext earlier this year or early last year, and by basically dissecting the very deep networks into small building blocks that can have efficient computations in them. And what these kind of network leads is that it inspires us to think about networks that are efficient in using the flops in it, and making sure that the models is really small and the performance still kept. We found a bunch of practical ideas that guided us to find smaller models. Seems that it's always better to go deeper. AlexNet is 7 layers and ResNet is often 50 layers or so, and that gives us a much better performance. Now, it seems that for applications, especially for style transfer type applications, we don't really need to go to very large layers. Often a very small number of channels is already good enough. And then the depth of the model, well, actually, sorry, that was a typo. So the model size matters quite a bit. And for convolution filters, in practice, we found that it's almost never needed for us to go larger than 3x3 filters. Seems that 3x3 is a sweet spot that allows us to do very efficient, very high accuracy, as well as good optimizations using Winograd and things like that. And we essentially basically did kind of like a grad student decay kind of approach where we iterated on a bunch of models and landed up with a pretty small model that does the style transfer work. Now, when we're looking at the numerical implication of these models, one thing that we kind of started finding back in 2012 is that convolution and like matrix multiplication is basically the core of CNN computations. Over the last few years, we really optimized it very well on like GPUs and things like that. And that was basically one of the key driving forces for us to having larger models, right? And cuDNN has been improving the performance maybe like 5x or 10x. I really didn't count, but it was really great. And essentially, like what convolution does is it's basically taking these little patches from the images and mathematically laying it out into a big matrix and then just multiplying the expanded feature matrix with the filters, which can be represented as another matrix. And then we can use, like matrix multiplication and all those kind of numerical libraries to do it. We started doing these kind of things, and it has, huge implications. The memory footprint is huge. The computation time is not that efficient because if we think about the feature matrix, it's actually replicating a lot of the memory entries and things like that. So over the years, we kind of started like looking for and finding quite efficient algorithms to do it. And one thing that turned out to be very useful for us in the style transfer work and a bunch of mobile deep learning applications is to use optimized libraries such as NMPAC to like run those convolutions very efficiently. And one core algorithm that turned out to be very useful in NMPAC is called Winograd. And essentially, it uses a mathematical trick by converting the filter or the feature patches and the filter patches and to convert the convolution into basically element-wise multiplications that mathematically reduced the number of flops by 2.5 times, if I recall correctly. And NMPAC is actually written by one of our pretty awesome interns, Marat, and I actually saw Marat down there. Hey, Marat. And those kind of things really helped us to drive up the performance quite a bit. Now, on the other side, the other thing is on the mobile side, we're kind of starting to see quite a lot of like very nice computation capability presented by the specialized hardware, such as iPhone GPUs. And in Caffe2, we basically employed metal kernels and MPSCNN from Apple to run the convolution networks whenever there is like an iPhone GPU present, and that actually makes the runtime much faster. It gives us a huge power saving, and then all these code are already open sourced if you want to check it out, and it's on the Caffe2 repository, both the NMPAC one and also the iPhone GPU one. So then the last thing that we found very interesting is that those models are sometimes too very big for us to deploy on the phones. And there was a very nice paper from ICLR from Son Han from Stanford that talks about the way, talks about ways for us to prune down the parameters, to quantize the parameters to lower bits, and then to even like zip them to an even smaller size. And that we employed that to basically reduce the model size to sometimes like 4 to 5 times or 6 times, something like that, which then allows us to very efficiently deploy those models onto the phones. What we did is, for example, when we are running the computation, we could do runtime decompression of the parameters and use them and discard them on the fly so that we keep a very small memory footprint even for very large models. And all these kind of things essentially led us from, that little cute box to a very high definition real-time neural style transfer model that can run real-time on the phone about, 20 FPS on a modern iPhone 7. And we can also use deep learning to do a bunch of other little tricks, such as using gestures to control the style switch, and to do like smile detections to take a photo and things like that. Essentially, basically, by combining all these kind of technology, we're able to make in the past like deep learning models that have to run on very beefy machines to the mobile side and running them real time to augment quite a bunch of the camera lens that we're having on all our phones. So all these kind of things are already open source online, and we're going to be talking a little bit more deeper, like with how we do training and how we do mobile development with Puya and Bram's talks. And I think the next thing that will be interesting to talk about is, what kind of directions we're looking into and what directions we think are going to be pretty valuable to have. One thing that comes up immediately is, like today we need to do a lot of distributed training. And one of the biggest complaint that we got from Caffe is that it doesn't support distributed training. And so we we were working on distributed training, especially using computer vision, things like that, quite a bit. And the thing we found is that we're kind of gradually converging into that classical scientific computation model, which is MPI, or message processing interface. And it used to be thought as, like this really old school thing that only lives in national labs and things like that when you do weather systems. But it turns out that it's a very good abstraction for machine learning, especially when we're doing Syncast 3D, which we do for every deep learning application, every like CNN training application, then they basically just adopt an MPI-like fashion. What does it do is, let's say we have 3-layer network. It runs the forward pass, it runs the backward pass, and then we run the update for the parameters, right? This is one single machine. And if we have multiple machines, what happens is there are reduction and operators that are being inserted before we update the parameters. And what they do is they collect the gradients that are generated from each worker or each GPU or each machine, and then we basically sum them together across all those machines so that when we update the parameters, the different models or different replicas basically start with the same parameter, updates the same gradients, and then gets the same updates. And now, if like the conventional computer science wisdom basically tells us that we can basically do the pipelining kind of tricks by starting communicating the parameters immediately when we have the gradients ready after the backward pass of each layer. And that effectively hides a lot of latency that we are observing during training, and that gives us a very nice linear speedup, basically. Now, we developed this library called Glue because, honestly speaking, inside Facebook, like deploying MPI becomes a little bit tricky because the old school MPI, like scheduling and machine management kind of mechanisms, is a little bit tricky. So we wrote a library called Glue that allows us to implement MPI-like collectives such as all reduce and broadcast without having to drag along a very big MPI runtime. And it's written by Peter, who is a pretty awesome engineer from us. He's also the creator of Redis, if you like Redis. And we also open source that. Glue also supports, like integration with Nickel, which is NVIDIA's distributed communication library. And we're using Glue to basically drive a bunch of distributed training jobs. So we're actually preparing a tech report to kind of like share more details about how we use distributed training to train very large ImageNet models at a very short time. Before that tech report is out, I was told to not share too much, but it's going to be coming out in 2 weeks or so. So stay tuned. We're really excited to share that, and I think that will help. That will help a lot of us to like train models really efficiently. So the other thing that we kind of like found to be very interesting is, we did quite a bunch of optimizations to kind of take a model and then figure out before runtime what kind of things we can save. Now, if we run on Android phones and iOS phones, one thing that we found is that memory allocation and deallocation becomes extremely expensive. And now there's this trade-off. In the Caffe days, we basically explicitly lay out all those kind of intermediate results without reusing the buffers, causing a huge memory consumption. And we could also do it in a dynamic way, where we basically deallocate memory whenever an intermediate result is done. But without a memory pool, what we found is that sometimes it causes us, like 30% to maybe 70% of the overhead, because memory allocation and deallocation is very expensive. So one thing that we had inside Caffe2 called Memonga is basically implementing this trick that we look at the lifetime of each intermediate results, like when it gets started to be used, when it finishes being used, and then we can basically do a register coloring kind of algorithm to figure out how many buffers we need and what kind of intermediate results are going to be sharing which intermediate buffer. And what that leads us is essentially we have the minimum needed memory allocated. We don't need to deallocate and reallocate memory all the time, and that gives us a very stable runtime, a very efficient runtime on the mobile platforms. The other thing that we looked into pretty keenly, and Puya is probably going to be talking more about this, is quantized computation. So far, a lot of the applications that we're running on is using float numbers, right? And float is in some way pretty luxurious. What I'm showing here is, like the number of exponent bits and the number of mantissa bits that are in, respectively, in different data formats. So a float has 23 bits to represent the actual number. And if you think about deep learning applications, we're already very sloppy in the sense that, like all those kind of models are initialized with random numbers. They're trained with stochastic gradient descent. We don't really know what kind of data and order we're feeding in and things like that. Every time we train, we end up with a different model, different parameters, although they perform slightly different, well, they perform almost the same. Now, that kind of gives us confidence that, by reducing the precision down to, let's say, 16-bit or, like even use fixed int8 computations, it could potentially give us a pretty nice gain. And from two fronts. One is, like bandwidth becomes much better. If your algorithm is bandwidth, like memory bounded, then instead of transmitting a 32-bit number, you just need to transmit a 16-bit or 8-bit, which gets much faster. And if there are hardware support for fast, reduced precision or int computations, then we can definitely utilize that for us, like to have an even faster runtime. So that's one direction that we're looking into pretty actively, and we hope to have more like things to share down the road when we find them. The other thing that's kind of interesting is, like there's a bunch of ideas floating around about how we can do quote-unquote compiler technology or things like that. For example, TensorRT is a pretty nice example showing that once we fix a model, we could do a lot of graph manipulation by like merging operators, merging different kind of, like, for example, like merging convolution and value and things like that, and which would allow us to run models much faster than the old interpreter model where we have to separately run each operator and then waiting for them to finish to run the next and things like that. And as the chips and hardware becomes faster and faster, this seems to be more and more of an issue. One example is that, like for newest Volta GPUs, actually, like small operators such as batch normalization and value are actually starting to occupy a non-trivial amount of the computation time because they are I/O bounded and running them separately is just not efficient. And so by having ideas about compilers or basically like just-in-time compilation and things like that, we'll potentially be able to fold in computations such as a convolution followed by a value into one single computation that makes like all these activations and things like that come for free for us. And that will become much more important when we have much faster hardware and much bigger networks. I wanted to basically just like very quickly go through these ideas and then leave on like some more time for us to like discuss, what kind of needs we have and what kind of good and bad you have in trying out Caffe2. So honestly speaking, what happened is that like at Facebook, like internally, we have a slightly different build system and things like that than open source. So we tried really hard to make sure that the open source society gets very good support. As an example, for the build system, internally, we have a system called Bug, which is kind of, like it's open sourced, but it's like a very custom built build system for us to build the whole Facebook code base. And on the open source front, we thought instead of like forcing everyone to use Bug, we probably want to use the old school nice CMake systems and things like that. So we built a CMake system. We tried really hard to make sure it works. But honestly speaking, our fear is that we might not have tapped into the open source use cases good enough. And despite the fact that we tried really hard, that might be use cases and pain points that we overlooked. And one question that we would really love to get feedback about is, what are the features that you guys need most? What kind of things worked well? What kind of things didn't work well? And what's your suggestion for us to basically improve the framework and improve the open source engagement? And with this, I'll probably just leave it here. And I'm wondering if we can use like the next 15 minutes or so that I saved to discuss a little bit of like what kind of pain points we have. Any questions? Here.
Basically, the question is about internal representation of a model. So TensorFlow has this nice XLA representation. Do you have anything like that in Caffe2?
So right now, we haven't really, have a full-fledged compiler unit into it. And we kind of basically provide interfaces to, vendor libraries such as TensorRT. And on the mobile side, we have worked with Qualcomm on their Snapdragon neural processing engine. Working together with FAIR, we're actually kind of looking into these kind of technology, hopefully sharing, the underlying library with PyTorch and Caffe2. And it's very early stage right now, so I don't really have too much technical details that we can share. But as the progresses, like in a few months, I'm sure we'll have more things contribute, pushing out to the open source side on this front.
So yeah, my question is about model compression. So when you do model compression, your, I guess, weights become irregular. And as far as I know, the Apple library and the Cudian, they don't have good support for sparse weights. I mean, how do you handle that?
So this is a very good question. So right now what we do is we actually do model compression for storage. And like all these kind of model compression approaches today, and often lends us a model which is what we joke as semi-sparse. It's not like in the conventional sparse matrix sense, which is like say 1 to 2% sparse. It's often like 30% or 50%. And as a result, this sparsity is not like big enough for us to utilize the conventional sparse math libraries, and we pretty much basically use it use model compression to store the parameters. But then once we do computation, we kind of convert them back to like the dense kind of sense, just ignoring the zeros in there, and do the computation like that. I think if we have libraries like numerical libraries that can utilize those kind of sparsity patterns, that would be definitely pretty awesome. I'm kind of wondering maybe offline we can chat with Marat on what kind of ideas he has on that and things like that. Pretty nice. Maybe we can have a break and then we can come back to listen to Priya's talk.